Okay, so now we're going to be talking about Ohm's law, which is the simplest form of circuit analysis that models the current voltage relationship between uh, different passive elements. So, generally, though, Ohm's law is derived from a relation between the current density and the electric field. But the simplification leads to the voltage being equal to the resistance times the current. And in general, this leads to talking about the voltage current relationship. If we, based on this equation, the the voltage divided by the current gives us the resistance. And this tells us that the model for some kind of resistor element is very linear. And we can actually extend this to impedance, which we'll cover later on. But just in general, Ohm's law models a voltage current relationship which describes resistance of an element. More voltage means we have higher resistance, or maybe less current leads to higher resistance. That's the idea of it. And that's the idea just of Ohm's law. Now, of course, Ohm's law doesn't actually just get uh, isn't limited to just talking about resistance. In a way, we can model a voltage current relationship for a capacitor like so. Or actually, it's more like it looks like this, that the current is equal to the capacitance times dV dt. So the change in voltage creates uh, current through a capacitor. Similarly, a voltage across an inductor is created by a change in current. And so these technically are variations of Ohm's law. However, when we kind of see later on, this there's no intuitive direction for this until we convert it to phasor. In which case, VC is equal to XC, which is just the reactance times the current. Something of that form. And then this, similarly, is VL equals XLI. Of course, this is not the formula, but notice that we can model in phasor a form similar to what was given with Ohm's law. And that's actually what leads to a generalization with Kirchhoff's voltage law and Kirchhoff's current law, which we'll be discussing next.